The first thing that I need to do is actually talk about what it means for a set to be countable or listable. And that will kind of form the bedrock for what we're going to talk about in terms of your Cantor's thinking. Okay. So what does it mean to be countable or listable? Okay. Well, it means that you can literally list the elements of that set. Yes? So what about the positive integers? Okay, z plus, which of course is just the set consisting of 1, 2, 3, etc. Is that set listable? Yes. We just did it, didn't we? We went 1, 2, 3, etc. Yeah? Listable means that you can literally write down a sequential list of the elements in the set. Okay? So the set of positive integers is listable. What about the set of natural numbers? Is that listable? Sure, right? I mean, in fact, the way that we write it down indicates that it really is. Okay? Basically, I mean, the only thing we add is the number 0, and all we did is we shifted everything down. Yes? Now, what about the regular old integers? Okay? The regular old integers consist of both positive and negative integers and 0 itself. Is that a listable set? Okay, how would you list the elements of that set? Okay, because I mean, there are some bad ways you could list the elements of that set. What listable means that you need to eventually be able to get to everything in that set. The way that you list it is critical to that end. You need to be able to actually list everything sequentially so that you reach every element in the set. Yeah. Okay, right. Yeah, so yes, Zach. Oh, right, the same idea. Basically, you start with 0, and then you kind of alternate between pluses and minuses, yes? And that guarantees, I mean, you can give me any number you want, 1 trillion. Well, I'm going to get there eventually. You see what I'm saying? What about negative 1 trillion? Well, that's right next to 1 trillion, yeah? In the way that I list these things. Now, there are bad ways to list the integers where you wouldn't necessarily reach everything in your list. Does that make sense? Like if I first decided to list the positive integers, would I ever stop? No. And there would be no guarantee. In fact, I would never even reach a negative integer. But if I kind of interleave them together, dovetail them together, then eventually I will reach everything in the list. Okay, so here's how I would list these things. 0, you guys were saying 1, -1, 2, -2, etc. Yeah? Okay, so these are some listable sets. Listable, basically what it amounts to, and this is going to sound kind of weird, it amounts to us putting the elements of the set in bijection with the positive integers. Because basically what we're doing is we're counting these things sequentially. We're saying, okay, in this case, 0 is the first element, yes? 1 is the second element, okay? -1 is the third element in this list, yes? And there's actually kind of a one-to-one correspondence between the positive integers and these things. I can literally talk about which element I'm at in my list, yes? So listable means that there is a bijection between the positive integers and the set that we're dealing with, yeah? Does that kind of make sense? Okay, any questions on that? And let me just say that what we're going to see is it was your Cantor's idea that this was an effective way of kind of counting the elements in the set, counting the elements in a set, even if the set happens to have an infinite number of things in it, okay? I mean, for instance, if I had the letters A, B, and C, and that was in my set, how would I know how many elements there are in there? Well, essentially what you do just as a human being is you say, well, 1, 2, 3. And do you realize that you're creating a bijection between the set 1, 2, 3 and the set ABC when you do that? when you do the act of actually listing those things out, you're literally counting the elements in that set. And so what Cantor did was try to extend that to infinite sets. How would I go about counting these things? Well, that just means I'm putting them in bijection with the positive integers, yes? Does that make sense, hopefully? So listable, countable, sometimes it's called countably infinite, okay? And this really is kind of the baseline size of an infinite set. How could there be a smaller infinite set? I mean, all we did is we just started counting and then we just never stopped. Does that make sense? There couldn't be a smaller infinite set than this. All we did was we decided to start counting one day and we just never stopped, yeah? So a countably infinite set is kind of the baseline level of infinity, all right? Okay, so that said, let us move on to the presentation proper, okay? So let me kind of hide this thing. Okay, let's talk about the transfinite realm a little bit here, okay? So here's one that's maybe not as intuitive, and you guys actually saw this, I think, in Heart of Mathematics, correct? Q, what is Q again? What's the notation Q stand for? Yeah. Rational numbers. What is a rational number, just to make sure we're on the same page? Yeah. Yeah, a number that can be expressed as a ratio of integers, specifically, yes? Either positive or negative. And at first you might think to yourself, good grief, there's no way that the rationals is going to be a listable set. In fact, the integers sit inside of the rational numbers. Do you know what I'm saying? The integers are literally inside of the rational numbers. And there's a lot more rational numbers than integers, or at least it looks like there are. But when we think about it carefully, it turns out we can actually list every rational number in a way similar to what we did for the integers. So how do I do this? Well, what you do you guys see how this thing has been constructed? Essentially, what I've done is, you see there's like 0, 1, -1, 2, -2. I've kind of listed the integers in the way that we just did back there. But the first row, I've written all of the ratios of integers that have 1 in the denominator. Do you see that? It's all the ones that have 1 in the denominator. What about the second row? Those are all of the ratios of integers that have 2 in the denominator. Do you see what I'm saying? Okay, what about the third row? Those are all the ones that have 3 in the denominator. All right? Is that true? Hang on a second. So wait, 1, 2, so how is this thing being listed here? 1 over 1?
We just took out the ones that got duplicated.
We took out the ones that it's going, how's it going here? Hang on a second. 1, 2, 3, 4, 5, 6, 7, 8. Oh, okay, yeah, I'm just taking out the ones that actually got duplicated, yes? But the whole thing is, I can actually get to any one of these things. The way that I was just talking about it, I could have also listed it that way, right? I can get to any one of these rational numbers by snaking through this thing in this way. Do you see that? You say, hey, my favorite rational number is like 3,742 over negative 7,238. Well, by snaking into that like infinite array far enough, I'm going to eventually reach that thing. Do you see that? So the rational numbers are literally a listable entity. That's kind of interesting for sure. Well, what if I take, okay, and what we're doing is I'm kind of following the logic of Cantor here, okay? What if I take one listable set and another listable set, and I compute the Cartesian product of the two? Remember, what is the Cartesian product again of two sets? Yeah.
You give like one element can go with every single other element, and that's like a subset. And then you have the next element is paired with every other.
That's right. So that's right. So it's the set of all possible ordered pairs of those things. Does that make sense? So it's a set of all ordered pairs of elements from these sets. Now, you might think, that if I take one countable set and another countable set and I form the Cartesian product of the two, that I might not be able to list the things anymore. Does that make sense? But you can. And the way you do it, okay, let's make sure that we actually describe accurately how we're doing this. You see that the first column starting at the bottom, those are all of the, right? The first column starting at the bottom, those are all of the ordered pairs that have A1 as the first element, yes? The second column is all of those that have A2 as the first element, etc. And how do I list these things in such a way that I can visit every single one of these ordered pairs? You just snake through in the same way you did with the rational numbers. Yeah? I think that's kind of slick, right? And by the way, what if I just slap on another countable set? Well, I know I can list all of these ordered pairs, right? There's a way of effectively listing all of these. And so that would just be, I would basically just go through the same process again. I would put the ordered pairs down like the rows or something like that. And then I would have the third new listable set down below, and I would still be able to snake through these things. So that the one thing that's kind of surprising, and it surprised Cantor as well, is there literally, there's no stopping us here. I could have 78 countable sets. I can compute the Cartesian product of all of them. That is basically 78 tuples of things. And that set is still listable. Yeah? So what do you think Cantor eventually started thinking? There's probably not a set that isn't countable. Yes? Probably everything is countable. So I just want to talk about something. So we have several denumerable sets, okay? So denumerable is another term that's often used, okay? Denumerable literally means listable or countably infinite, okay? So denumerable means listable or countably infinite, just so that you're aware. Okay? It means like basically there's a way to kind of enumerate these things, the way that we've been doing. Okay, so we have the natural numbers, the integers, the rational numbers, even Cartesian products of countable things. And by the way that you notate the size of these things is with like absolute values, okay? And I realize that these sets have an infinite number of elements in them. You can still talk about the so-called cardinality or size of these things. And so the big question is, are there non-denumerable sets? Are there things that cannot be listed in this way? Okay, what about the real numbers? Well, let's talk about that for a minute. Okay, do you guys remember what I stands for? Maybe we haven't used that notation, but I'm letting stand for the irrational numbers, yes? So Q is the rational numbers, I is the irrational numbers. And of course, any real number is either rational or irrational, yeah? Okay, so the real numbers is literally made up of kind of the combination of these two things. Now, upon first glance, you might think, well, of course, you know, the real numbers, basically half of them are the rationals and half of them are the irrationals or something, yeah? That might be what you think intuitively. But it turns out there's kind of a surprise around the corner here, okay? So, and it turns out there's this notion of denseness of the rationals and the irrationals and the real numbers. That is, if you take any interval in the real numbers, guess what you're guaranteed to find in there? Both rationals and irrationals, okay? That's what dense means. So I don't care how tiny of an interval you take, you're going to find rationals and irrationals in there every time. And by the way, even if you take a couple of rational numbers, there will always be an irrational between them. And vice versa. If I take a couple of irrational numbers, guess what will always be between them? A rational number. That's what dense means. So, I mean, when you see something like that, you might say to yourself, oh man, these things have to be basically the same size, correct? They seem to be so interwoven with each other in the fabric of the real numbers that there doesn't seem any way to get around the fact that they probably are the same size. But we're gonna find out that that is not the case. All right. So let's just talk this through a little bit. If both the rationals and the irrationals were both denumerable, then the real numbers would also be denumerable. Does that make sense? If the rationals and irrationals could both be listed, then the real numbers could be listed. Why? Can you guys give me a good reason for why that would be the case? Yeah, over here, yeah, Colby.
Because of every single element of, if Q and I make up R, every single element of Q and I can be like listed. And obviously all of R would be listed because all of these elements would be listed.
Okay, so how would you list the combination of the rationals and irrationals so that you could see that? Yeah, Ivan?
You could just do like the first element of each together. And
Yeah.
The second element of each together. And then the
That's
third.
right. Kind of like what we did with the integers, where we like went positive, negative, positive. We kind of alternated between the two positive and negative sets. We could do the same thing here. You would just kind of alternate between rationals and irrationals. Okay. So like if I had Q and I was able to list those things, I say, okay, Q1 is the first rational, Q2 is the second rational, Q3 is the third rational, I1 is the first irrational, I2 is the second irrational, etc. In my lists, then I could just interweave those two to get a listing of the real numbers. Does that make sense? So that was the suggestion. You would kind of jump back and forth between a rational and an irrational. And in this way, we would be guaranteed to reach every possible real number eventually. Yes? So you say, my favorite number is pi squared over 6. Well, eventually I would reach that thing, right? Because those two lists guaranteed the systematic listing of every rational and every irrational, and I've just interweaving those together, and I would reach pi squared over 6 eventually. Yeah? All right. Since we already know that Q is denumerable, right? We already know that. The denumerability of the irrationals would imply that of the real numbers. Yes, that's kind of what we're saying here. So if I were denumerable or listable, then R would be denumerable or listable. Yeah? On the other hand, so this is looking at the converse, we've talked about logic a little bit. If R were denumerable, that would imply that I would be denumerable as well, because after all, I sits properly inside the real numbers. Yes? So what we've done here is we have like an if and only if statement at this point. Yes? We kind of have the rationals already on the side as being a listable entity. And what we've said is, if I is listable, so is R. If R is listable, so is I. Does that make sense? So it's an if and only if. So R is denumerable if and only if I happens to be denumerable. Okay, but there are some problems. Okay, first of all, our intuition says that the rationals and irrationals should have the same size. However, a couple of things happened in the mid-1800s that made mathematicians start to speculate that something interesting was going on. Okay, and in particular, I will mention there was a mathematician by the name of Weierstrass, who really started to kind of take what Newton had done with calculus and push it to its limits, literally, okay? And he actually found that there was a function that was continuous on the irrationals. You know what continuous means? Yeah? So it turns out there's a rigorous way to define what continuous means. But it was continuous on the irrationals, but discontinuous on the rationals. So that is, at every irrational number, the function was continuous. But on every rational number, you had a point of discontinuity. Does that make sense? Okay. So the irrational numbers, the function was continuous there. But then there was like jumps happening at every rational number. Yes? So the graph was behaving in a continuous way on the irrationals, but there were jumps on the rationals. So he came up with an example of such a thing, okay? And it's actually not that hard of a function to digest, but then second, Weierstrass actually showed that there was no function that behaved in the opposite way. That is, that was discontinuous on the irrationals, but continuous on the rationals. Yeah? So if the irrationals and the rationals were really behaving in the same way, it doesn't seem like it would be possible to do such a thing, Okay. Okay, and so that's where things start to get weird. So again, this seemed to fly in the face of intuition concerning any sort of symmetrical relationship between the irrationals and rationals. Okay, somehow we're able to build a function that's continuous on the irrationals, but not on the rationals. But I can't do the opposite. Yeah.
What do you mean function of the rationals?
So a function like of x on the real numbers, and every time, like at any point that was an irrational number, the function was continuous there. So the graph, you could draw it like without picking up your pencil through that point.
Yeah, like I get the continuous part. I just don't understand how you would make a function of the irrational numbers. Because you can't even list them. So like, how did you get there?
Well, yeah, you can't list them, but what he basically did, it was kind of like a piecewise defined function where he just said, do this whenever the number is irrational and do this other thing whenever it's rational. Okay. We can definitely talk about that. That's an interesting example. We'll talk about that probably by the end of the term or something. We'll look at Weierstrass's function. Okay. So during this rapid development of calculus at the time, limits had definitely served their purpose, but it was becoming clear that to advance further, the study of sets was going to be a needful path forward, right? And that's why we were just talking about sets a lot, okay? Thinking about sets is really one of the bread and butter topics of mathematics, and it has been so for the better part of a century and a half at this point. Okay? So your Cantor, some people say George. I think technically the pronunciation is Gior, but I'll just call him Cantor from this point on. Again, born in the mid-19th century, moved to Germany when he was 12, very religious individual, okay? His father actually converted from Judaism to Protestant Christianity, but his mother was a Roman Catholic, which is interesting, yeah? And he was very interested in theological systems for good reason. I mean, he was kind of trying to discern what is the difference between what you believe, Mom, and what you believe, Dad, right? What's going on here? I mean, you know, there's going to be a lot of conflict there with those two belief systems. He was like, so, I mean, that's kind of like an axiomatic system sort of thinking. You see what I'm saying? I mean, he's kind of looking at a core set of beliefs and developing a theological system from both and looking at the contrast between the two. But eventually he got obsessed with infinity, just literally obsessed with infinity. Okay, and it was basically his idea to count the size of sets through bijective correspondence. So like, remember I said A, B, C, 1, 2, 3, right? Like, how do you know that the set ABC has 3 elements in it? Well, you basically count them, 1, 2, 3. What you're doing is you're setting up a correspondence between the number 1, 2, and 3 with each one of those elements, yes? So bijective correspondence was his idea. So really that removed the need to really count anything. You could just create a function that kind of did the counting automatically. Basically would create a function that was bijection between the positive integers and the set at hand, okay? Right, counting, as it turns out, is a more sophisticated and unnecessarily complicated way to quantify set sizes. If you could just produce a function that did that automatically, that's a better way to proceed. So again, what's a bijection? Just to make sure we're on the same page. We talked about that last time. What is a bijection? Yeah, Joseph. Yeah, well, it's a one-to-one correspondence. What are the two words? Like, so one-to-one and onto, right? One-to-one and onto. Okay, there's no two things going to one thing, and everything that is kind of in the codomain is hit by something in the domain. Yes, by the function. Okay, so those were kind of the two things that we had. This is a quote from Cantor in 1867. Okay, now remember, I said he was born in 1845, 1867. He's 22 at this point. Does that make sense? Yeah? This is where he's really starting to think things through carefully. You see this picture I've drawn right here? It's kind of like this correspondence between sets. This is the way he thought about everything. He said 2 sets, M and M, are numerically equivalent if it is possible to put them by some law in such a relation to one another that to every element of each one of them corresponds one and only one element of the other. That is the definition of bijection, isn't it? One-to-one and onto. And that's what it means to be in one-to-one correspondence with one another. Any questions on this so far? Okay, so this is Cantor. He's an interesting guy. All right, I want to talk about some of the naysayers, okay? Because there were some big ones. Okay, this was sort of a new path that was being forged in mathematics. Now, since the Greeks, the philosophers and mathematicians from ancient times had only considered things like the potentially infinite. Okay, so I mean, they could kind of see a set growing and expanding, but there was just the potential to become infinite. Does that make sense? Like it would grow and eventually it would become infinite. Like we just get tired eventually and stop trying to expand it anymore. Yeah. But Cantor's predecessors objected to the so-called completed infinite. Okay. So ever regarding that process to being finished at all. So like looking at the entire infinite set itself as an entity that was completed, that was mathematical heresy, okay? The completed infinite itself was theoretical pie in the sky, okay? Said another way, it was perfectly acceptable to explore the collection of the natural numbers from within the set itself. Like I can look at certain natural numbers and talk about their properties. I could talk about the ones that are divisible by 5. I could talk about how they factor. I could talk about prime numbers. But to manipulate the set itself was not good. Okay? That was something that would have not been accepted up until that point in time. Manipulating n in its entirety was tantamount to mathematical treason. Okay? But Cantor was perfectly willing to engage in this activity. Okay? So this was a new path that he was forging. And actually, he paid a pretty big price. He was basically an island unto himself. He was kind of ostracized from the mathematical community for a time. And in particular, do you guys know who that is? Anybody know? You guys see that picture of that little bell-shaped curve right there? By the way, that's the old German Deutschmark. Yeah, before the European Union was forged, right? And they went to the Euro system, but that's the old German Deutschmark. Yeah. Nope, it's not Euler.
Gauss?
Yeah, yes. That's Gauss. Yeah, Carl Friedrich Gauss. One of the most prominent mathematicians of the day, for sure. He basically developed kind of the underpinnings of probability and statistics, right? He's responsible for the bell-shaped curve, okay? Started looking at things like the normal distribution and moving us toward the so-called central limit theorem. It's a really big deal. And he did a lot of other things too. Here's what he said. As a CF Gauss, he said, I protest above all against the use of an infinite quantity as a completed one, which in mathematics is never allowed, right? That's a bold proclamation, right? You cannot take a set and just start messing around with it, okay? The infinite is only a manner of speaking. So he was, right? I mean, this is like the mathematician of the day basically saying you can't do such a thing. You can't just mess with a set in its own right. Okay, but let's talk about Cantor a little bit more. So this was kind of his approach, okay? So he used the natural numbers, and by the way, for Cantor, the natural numbers started at 1, okay? I know in here we've been starting the natural numbers at 0. We have some computer scientists in our midst. That's fine. I actually like including 0. But to him, the natural numbers is just the positive integers. And that would make sense because where would he start his counting? 1, 2, 3, etc. Yes? Okay. So the natural numbers was kind of the benchmark for the start of an infinite set, because after all, it makes sense that there wouldn't be a smaller infinite set than that, right? I mean, what smaller infinite set could you get other than just counting and then never stopping? Yeah, that seems like a good benchmark. He actually used this Greek letter right here. Does anybody know what that letter is? Yeah, that's Aleph. That's or not Greek, Hebrew. Yeah, Aleph sub-zero, Aleph naught, Okay, and it makes sense that he would do that. I mean, remember, he kind of grew up in a Jewish family. Does that make sense? Yeah, his dad was a Jew that converted to Protestant Christianity. Okay, so he used all if not to represent the number of elements in the natural numbers. To him, that was kind of like the baseline level of infinity. They called it all if not. Okay, sets of that size were called denumerable. And he would have written things like the size of the natural numbers is equal to the size of the integers, which is also the size of the rational numbers, which is all if not. Okay. He showed that lots of other sets had that size as well. I mean, he just was desperately trying to seek something that wasn't. Okay? Even the Cartesian product of two denumerable sets, as we've already seen. Okay? In fact, he was starting to wonder if there was ever going to be a set that he stumbled upon that wasn't listable. Yeah? Okay? And he finally did find one. Turns out that if you look at even an interval in the real numbers, even an interval, it's not possible to list it. Okay? And he called that set, he called that the continuum. Okay? So the continuum was what he called that. So any interval of the form A to B, like it doesn't really matter if you include the endpoints or not. It turns out that any interval is not going to be a listable set. Just sort of interesting. Okay? So here is Cantor's great theorem. It's called like the non-denumerability of the continuum. And actually his argument is right here in this picture. The entire argument is right there. It's almost like a proof by picture. Okay? So the great theorem is that the real numbers are not countable. They're not listable. Okay? And the way he's going to do that is by literally just looking at the numbers between 0 and 1, for instance. Okay? What he said is, well, I don't know. Let's assume that they are listable. In fact, right here, I mean, I know that there are numbers that are beyond, like you see these numbers right here of 8, 7, 5, et cetera, like that, right? But the key to the argument is really the decimal points that are kind of going down the diagonal right here. Okay? So what he's going to do is he says, suppose that they are listable. So what kind of a proof is this, by the way? It's a proof by contradiction. Yeah? He's saying, suppose I have a list. And then he goes, well, I am going to show that there is a number that's not in the list. How? Well, I'm going to stare at, you see the things that are kind of highlighted in gray right there? I'm going to stare at those. And I'm going to construct a number that is different from every number in the list by doing what? By like, instead of having 4 in the first position after the decimal, just pick something else. 5. Okay, go down to the next one, number 2. I have a 0 in the second position, right? So what am I going to do to make sure it's different there? Not have it be 0, like 1 or something. I have lots of options here, yeah? The third row, third position is 5. So I'm going to change that. I'm going to change that to like, I don't know, 7 or something. And do you see how you can go down that diagonal and basically construct a number whose first position is different from the first position of the first number, whose second position is different from the second position of the second number, etc., all the way down. Now, could that number that he constructed, could that possibly be in the list? No. How? What, could it be the first number? No, because it's different where? In the first position. Could it be the second number? Nope, because it's different where? Second position. Could it be the 8 trillionth number? No, because it would be different where? In the 8 trillionth position. You see what I'm saying here? And so Cantor said, I have a real number that is not in that list, which is a contradiction, isn't it? Because what did we assume at the beginning? Everything is in that list. Does that make sense? And he just came up with something. And you might say, right, or Monique might come up and say, yeah, but just put that number in the list. Seriously, yeah? Put it right at the beginning. I just kind of slide everything down and put that number right at the beginning. But then what would Cantor do right away? He would just make the diagonal again and say, well, I can find another one. Here we go again. Put that diagonal in there. I'm going to construct a number that's different in the first slot for the first number, second slot for the second number, etc. So no matter how many times you play this game of, well, fine, put it at the beginning, he can continue to find a number that can't possibly be in that list. Does that make sense? This is known as Cantor's diagonalization argument. Okay? It's a very famous argument, very simple, but what it shows is that there's no way to list the real numbers. Yeah? So we assumed there was, and then we got in trouble. Okay, and so that's a proof by contradiction. We got in trouble at the end, therefore the fault in our assumption was that we could have listed them at all. It's not possible to list the real numbers. Any questions on that? Questions? Okay, we're actually almost done. Like this picture right here, I mean, this is, I have uploaded this slide presentation into Canvas, but this picture right here is actually a way, see that how that's like one high over there, okay, on the left, the dotted line right there. This picture right here shows a way to kind of put the numbers between 0 and 1 in bijective correspondence with the positive real numbers. Do you see that? As you kind of shine a light, you draw a straight line from P through over to X, and you have a number right there between 0 and 1 that's kind of the image of X. This is a way to actually put the positive real numbers in correspondence with the numbers between 0 and 1. In other words, there are the same number of numbers in terms of infinity between 0 and 1 as there are between 0 and infinity, because you can put them in bijective correspondence. Okay, that's sort of weird. Yeah, I think that's pretty weird. I think it's also kind of neat though. Okay, so the size of the real numbers is really just the size of 0, 1. Okay, I mean, actually the size of the real numbers is the size of any interval in terms of thinking about it as a completed set. Okay, so that's sort of weird. Let's talk about the so-called power set theorem. Do you guys remember the power set of a set? What's the power set of a set? All the subsets of a set, yes? All the subsets of a given set. There's something called the power set theorem. This is also Cantor's theorem that says, you give me any set, infinite or not, its size is going to be strictly less than the size of its power set. That was definitely true for finite sets, wasn't it? Remember what was happening? I mean, like, I think Monique talked us through this. If I started with a set with like 3 elements in it, and I constructed its power set, how many elements were in that? You remember? 2 to the 3rd, remember that? So it grew. And it turns out that's also true when it comes to infinite sets. You start with an infinite set, you compute its power set, you will get a strictly larger set. Strictly larger, a set that cannot be put in bijective correspondence. Yeah.
So when you did the Cartesian product, though, it seemed like it should get bigger as well. And so is there some sort of point in between these where it would cross over between?
Well, that was the exact, okay, so you're saying, is there some kind of point at which you keep adding stuff and then you make this transition or something?
Yeah.
That was the question that Cantor had. And it literally drove him insane. Literally insane. Like went away into the loony bin, okay? Multiple times. So what you're asking is the question that Cantor tried to ask, and I'm going to get to that here in just a minute for sure, okay? So the size of A being less than the size of B means that there is an injection. What does injection mean? 1-to-1, but not necessarily onto, yes? That means you can put A inside of B, but there's no surjection from A to B. That is, there's no onto function from A to B. Does that make sense? Okay, that's the essence of what's going on with that. Yes, Maggie, do you have a question? Yeah, that's right.
That's 0 to 1 and onto.
That's right.
Injection is just 0 to 1.
1-to-1, 1-to-1.
1-to-1.
Yeah, injection is 1-to-1.
Okay.
Surjection is onto. Bijection is both.
Okay.
That makes sense?
Yeah.
Okay. So here's the idea of the proof of the power set theorem. The power set theorem basically says any set has size strictly smaller than its power set. Yeah. Any set, even an infinite one, has size strictly smaller than its power set. And here's the idea of the proof. He says, suppose I have a function going from the set to its power set. This is a weird function, by the way. The input is an element from the set. The output is a subset of that set. Yeah? It's sort of a weird thing. And we'll actually look at some examples of this on Monday for sure, just to clarify. But look at this set. B, I'm going to define it as the set of X belonging to A, such that X is not in its image over in the power set. It seems sort of weird, but we'll talk about that more later on. Okay? Have you guys ever seen like this like paradox where it says you have like a piece of paper where on one side it says the statement on the other side of this paper is true, and you flip it over and it says the statement on the other side of this paper is false. It turns out that what we're about to see right here is kind of like a version of that in some ways, okay? Hey, I construct the set, and we'll talk about this on Monday. I'm not going to go into it right now just because I want to get to the punchline here. But it turns out that set that I just defined, it's a subset of A, yes? It is a subset of A because it consists of elements in A, right? But the question is there anything from A that actually maps to this? Okay, and the answer is going to be no. And we'll have to think that through carefully together on Monday. Okay, so that'll be a fun little exercise on Monday though, okay? B is an element of the power set, but could there exist any element in A such that f of A is equal to B? And the answer to that question is no. And we'll see why on Monday that happens to be the case. That's a little cliffhanger for you, okay? But it means that this function cannot possibly be a surjection. It's only an injection. It's not onto, it's only one-to-one. Okay? The power set theorem basically implies that the size of the natural numbers is going to be strictly smaller than the size of its power set, right? Then what can I do after that? Take the power set of the power set, and that will be strictly bigger. And so what does that tell us about the number of levels of infinity for sets? There's infinitely many levels of infinity. It just gets bigger and bigger and bigger and bigger. Yeah? And I promise we'll return to this and kind of look more carefully at this, but I don't want to ruin your fun. Yeah, no. That's a great question. Go Google it. Google it and come back and tell us on Monday. That's a great question. What is the level of infinity of the number of levels of infinity? Yeah. Go Google that. See if Google blows up. Okay. All right. So this is the thing I want to end with. It's a so-called continuum hypothesis. Okay. Cantor was actually able to prove that the size of the real numbers was equal to the size of the power set of the natural numbers. Okay. Which is bigger than the size of the natural numbers, yes? But he wondered, and this is kind of along the lines of what Ivan was saying, he wondered whether it's possible to find a set that's between those two, yeah? Is there something that is strictly between, so like if I take any subset of the real numbers, for instance, is it always going to be the size of either the natural numbers or the real numbers? Or is it going to be something in between? Does that make sense? Yeah? And so the assertion that no such A exists is known as the continuum hypothesis, that there isn't a set that's between these two. Like if I take any subset of the real numbers, it will always have either the size of the natural numbers or the size of the real numbers, okay? An infinite set. Does that make sense? I'm only talking about infinite sets here, okay? And its proof eluded Cantor for his entire life, and he actually damaged himself mentally trying to prove or disprove it. In fact, there were multiple times where he was like, I proved it. And then he was like, oh, wait, no, I didn't. And he said, oh, wait, I disproved it. Oh, nope, there's a mistake there. And sometimes it was friends that were pointing it out. He was starting to gain some prominence. People were really checking what he was doing at this point. And he put himself literally in the loony bin on multiple occasions, okay? It was a bad situation. But then there was a man that came along in the early 20th century by the name of Kurt Gödel. You ever heard of this name before? one of the most prominent thinkers of the day. He was kind of a philosopher / mathematician. And he actually proved something called his incompleteness theorem, which basically says that if you are working in a mathematical axiomatic system that has the positive integers in it, then you're guaranteed to run across something called undecidable statements. That means statements that you cannot prove or disprove. And if you can't prove them and you can't disprove them, what choice do you have other than to just either accept them or reject them based on blind faith? Does that make sense? I can't prove them, can't disprove them. I have to just either accept it or reject it and then proceed forward. Mathematics had been totally resistant to that sort of thing up to this point. Okay? There wasn't, I mean, mathematics was like the black and white discipline. Do you know what I'm saying? And what Gödel did is he blew the lid off of that and showed that actually, if you just have the positive integers in your set, you're guaranteed to run across undecidable statements. Positive integers is pretty simple, right? Almost everything we do in mathematics has the positive integers in there and the things we would assume about them, yeah? And what Gödel said is you are guaranteed to run across undecidable statements. And guess what? Paul Cohen, 1964, a logician, showed that the continuum hypothesis, the thing that Gödel, or the thing that Cantor drove himself mad trying to prove or disprove for his entire life, is undecidable. It's an undecidable statement. Okay? So that's kind of an interesting conclusion to the story of Cantor by way of Gödel, and then much later on Cohen, right? Almost 100 years after the fact. But that is interesting. Do you think, I mean, just the last thing, do you think that's bad? Do you? Why do you think it's bad? Yeah, Ivan.
I think that means that Cantor was doomed.
Yeah, it's bad for Cantor. He was doomed to failure. There was no way he was going to be able to prove or disprove his statement, right? That's the essence of what Cohen was saying. It's probably why he found it so elusive in the first place, because he couldn't do it. Yeah? It was the worst thing. I mean, it was a bad problem for him to be working on. But from the perspective of like a Christian worldview, do you think this is bad? No. All it shows is there's nothing in the world that's impervious to faith. Yeah? I mean, even mathematics, we have to assume certain things. This is what this basically is saying. There are certain things that we have to assume and accept based on faith and faith alone, right? So I think that's sort of an interesting thing for us to learn from, for sure, as believers. Okay? All right. I'm done. We'll talk about the power set theorem on Monday and talk a little bit more about functions. And I'll have your test back to you on Monday.